Hi, I'm Professor Christina Pagel, and I'm going to talk to you today about the study we've been doing, which is using mathematics to inform where specialist children's retrieval teams should be located across England and Wales. So a bit of background into the project. It's called the DEPICT study, which stands for Differences in Access to Emergency Paediatric Intensive Care During Transport. And it all kind of came around because in 1997, paediatric intensive care units across England and Wales were centralised. And so there are only, between 25 and 30 paediatric intensive care units across England and Wales. And so what you then had developed was a service where you had what are called paediatric intensive care retrieval teams, PICRTs, providing intensive care to patients while transporting them from district general hospitals to PICUs. So a team would go out from a retrieval team location, go to the local hospital, start providing intensive care level treatment to the child at the bedside, and then transport that child back to the PICU. National guidelines say that teams must reach the bedside of the patient within 3 hours from accepting the referral. So here you can just see a quick overview of where they are. There are over 200 local hospitals given by the green dots, and then PICU locations in yellow, and then there are currently 11 different PICRT locations, all of which are located in a PICU. So the mathematical modelling workstream was trying to address how many retrieval team locations are needed to best serve England and Wales. So currently there are 11. So what we're trying to do is maximise the number of children reached within 3 hours of referral. Where should those locations be? So are the 11 current locations in the right place? And they do have to be at one of the PICU locations. And can a different configuration of locations or number of teams at each location help with surges in demand? So we know that demand is not even throughout the year. So are there things we can do to help address that? So here's kind of a retrieval team journey. The retrieval service accepts a local hospital request for transport for a patient. If a retrieval team is available, it then mobilises and heads out to the local hospital. Once the team arrives at the local hospital, they then spend some time stabilising that patient for transport. The patient is transported to PICU, which is not necessarily the nearest one. It can be one, say, where that child is typically treated if they have a chronic condition. And then after handover, the team then returns to the retrieval service base. So that's kind of how it's meant to work, and there are various things that you have to take into account when you're looking at this system. The first is that a team might not be available for transport, so then there might be a waiting time for a next team. And we have to also allow for the fact that there are different numbers of teams at each station. So although there are 11 locations, there might be different numbers of teams within each. And then you obviously have variable journey times. And in our mathematical modelling, we use kind of historical data from the service itself on how long journeys typically take between hospitals. And although we're kind of interested in the time to bedside, you have to take into account the other legs of the journey from the bedside to the receiving PICU and the journey from the PICU back to base, because that affects if a team is available for another transport. So you do have to take into account all parts of the journey. And finally, we know that there are different levels of demand by time of day and season. So daytime is busier than nighttime, and winter is busier than non-winter. So we took all of this into account and spent about 1.5 years developing a mathematical modelling optimization framework that was implemented using a genetic algorithm to be able to optimize not only where the location should be, but also how many teams you should have at each location. This is mathematical modelling, is currently under review, operations research in healthcare, And I'm not going to say any more about it, except that this is the framework that underpins the rest of this talk. So talking to our clinical partners in this grant, we developed various scenarios which we were going to then look at using the mathematical framework. So we know that demand varies by season and time of day. So we decided to consider just daytime because they're the highest demand. So if you have a service that works for daytime, you'll have a service that works for nighttime. But we did want to look particularly at 2 seasons, well, the winter, which is November, December, January, and non-winter, which is February to October. Winter here is chosen because the annual kind of surge in demand for paediatric intensive care is earlier than for adults. So it actually starts in November and not December. So that's why for us, winter is November, December, January. And we wanted to look at, we want to plan for the periods of highest demand, and we wanted also to see what if there was flexibility to add resource in winter, and what can we do to improve the current system. So currently in daytime, there are 11 locations and 16 teams. So on the right hand side, you can see kind of the 11 patches, which are all the DGHs covered by each of the 11 services. And there are 16 teams across those 11 locations. So in particular, we looked at the following. Can we improve time to bedside if we redistribute the 16 teams that there are among the current 11 locations? And then we looked at what if you redistribute the 16 teams among a reduced number of the current locations. So you don't change locations, but you think actually would it be more efficient to centralise that further? What would happen if we added teams in winter? So you don't change the locations because there's a lot of fixed infrastructure in a location, so you don't necessarily want to go changing that seasonally. But what if you could add teams, so you're adding resource to locations? And then finally we said, actually, is there a lot of benefit in completely revisiting where we put locations? Because if there is, perhaps that would be worth the restructure. So this are the results for non-winter daytime. So remember, this is February to October. On the y-axis is average time to bedside in minutes. On the x-axis is number of teams, and then the different coloured lines are different numbers of locations. So the red dot is 11 locations, the current 16 teams. That's where we are now. And this green dot is 11 locations, the same locations, but you're redistributing the teams. And you can see that actually you can get a large improvement just by changing where you put those teams across the 11 locations. By about 10 minutes, you can reduce the average time to bedside. But really, what you see is that once you've optimized where the teams are, the average time to bedside for 8, 9, 10 locations is actually very similar. And in fact, for all of these scenarios between 16 and 19 teams, between 8 and 11 locations, you've got somewhere between 97.8 and 98.9% of all demand reached within 3 hours for all these scenarios. So actually, there are lots of different ways you can configure your service to get a really high percentage of children reached. The small percentage not reached currently, because there are just 4 or 5 hospitals in England and Wales that are really far away from a PICU. And whatever you do, it's going to be extremely difficult to reach those children within 3 hours because they're just so far away. So now we look at winter, where demand for PICU typically doubles compared to non-winter. So here you can see that for the 11 current locations with the current 16 teams, the average time to bedside has gone up to about 125 minutes, which is 15 minutes more than it is in non-winter, which is 109 minutes. And that's just because you're less likely to have a team available, and so there's a longer waiting time. If you redistributed those 16 teams across the 11 locations, you'd get down to about 110 minutes, which is still 10 minutes slower than in non-winter, but that same distribution. But you do also now see quite a lot of variation in the number of locations. And as soon as you get to 8 locations, you get quite a big saving. And that's just the efficiency of being able to double up your number of teams in every location. And that's the standard result from queuing theory, is that as soon as you can have more servers per queue, in this case more teams per location, you get quite a big saving in waiting time. The other thing to notice is that once you get to 19 teams, so if you can add 3 teams compared to your summer allocation or non-winter allocation, you actually match the average time to bedside of 16 teams outside of winter, which is 100 minutes. So that's saying that actually, say you have 11 locations, your current locations, if you could add 3 more teams in winter, you could compensate for that extra surge. So now we're looking at the improvements, the absolute improvements compared to the current situation of 11 current locations, 16 current teams, daytime winter. So we're looking at the busiest period, again, because on the grounds that if you can optimize the busiest period, you'll optimize everything else. And so we're looking at these following changes. You take the current locations but reallocate the 16 teams optimally. You then see actually what if we just centralize further and have 8 out of those 11 locations but still keep 16 teams. Then we look for what happens if you then add 3 teams, because we saw that there was quite a big saving in adding 3 teams from non-winter to winter. What if you then looked at the current 11 locations with the best 19 teams? And that's because there are always sensitivities around centralizing further. So actually, is there any benefit in doing that? So that's the orange bars. And then finally, we looked at what if you could put the locations anywhere where there's an existing PICU with the best 19 teams. So you wanted to look at the incremental improvements that you get from each of these stages. So if you're looking at just a reduction in waiting time for a team, so that's how long do you have to wait for a team to be available in winter if you get a referral, then compared to currently, if you just change where the teams are, you get almost a 15-minute improvement. If you then actually centralize further, and this is where you get that extra benefit from doubling up in each location, you get almost 25-minute improvement. If you add another 3 teams, it goes up more. You get to almost half an hour improvement in average time to bedside. The current locations of 11 locations and best 19 teams, you actually get a slightly higher waiting time because not all teams will be able to have, or all locations will be able to have 2 teams. And then if you allow any number of locations, which is actually, it turns out is 10 is the best number, and the best 19 teams, again, you get a slight improvement there in waiting time. But it's not actually waiting time that we're trying to optimize. What we're trying to optimize is time to bedside. So if we look at that now, it's similar, except you'll see that the difference between 8 locations here and 11 locations is smaller than it was here. And that's because if you have more locations, you're actually closer to more hospitals. So some of the time that you have lost by needing to wait longer, you gain back because you're closer to the hospital. And that's why here, for any number of locations, best 19 teams, although your waiting time is slightly longer than for 8 locations, your journey time is shorter. And so that means that actually 10 locations and 19 teams is better in terms of time to bedside than it is for 8 locations. But you remember that the actual standard, the national standard, is to get to the bedside within 3 hours of referral. So if we look at the current situation in winter, it's about 86% to get there. Then you get quite a big improvement from any of these scenarios, but there's not a massive difference. So actually, you can see here, the current 11 locations, but with 3 extra teams than now, which is 19 teams and allocated optimally, you get almost the best. So you get almost the best improvement. So what does that mean? That means that there are many different configurations of service that allow the vast majority of children to be reached within 3 hours. And as I said before, the children that can't be reached within 3 hours tend to be the ones in hospitals that are just so far away from a PICU that they're there's almost never going to be a way you can get there within 3 hours by road. So that's things like, the very tip of Cornwall, the very tip of Norfolk. In general, the principle is that if you have more teams in fewer locations, it's more efficient in terms of waiting time than the same number of teams in more locations. And although 8 or 9 out of the current 11 locations works a little better, given the same number of teams, the differences aren't that high, and they're unlikely to be large enough to be worth the potential restructure. And then when we looked at if you could put locations anywhere, you actually don't get that much benefit. You do get an improvement, but you don't get a massive improvement. And the effort involved in setting up new locations really does seem unwarranted, given the small potential improvements in time to bedside or PICU. But we have shown that in winter, being able to allocate 3 extra teams across England and Wales, so just 1 extra each at 3 locations, would compensate for that extra surge in demand. And that's potentially quite an important finding. So finally, thank you for listening. If you have any questions or comments, please add them as a comment below the video, and there's more information at these websites. Thank you.